Hey everyone, welcome to the channel. Topic for today's video, one of the research paper that is published by Amazon. It's about Dynamo, which is NoSQL database. It is highly scalable, highly available, and eventually consistent data store. It performs very well under huge load. So it is being used a lot. If you see the day-to-day operations on the Amazon, like order management, cart management, order processing. So under the hood, Dynamo is being used. So how this Dynamo came into picture? What was the initial problems? Why our regular RDBMS database is not the best fit for this use case? So this research paper is going to give us the insight about that one. By now I also know about Dynamo. You might also know about the Dynamo, what is this, what it does, but what is the story behind? What are the different concepts under the hood that make it so good that it performs very well under huge load? There is no data loss. There is if in like under the hood, it is a distributed system, right? So how it performs well when there is any failure or sort of things, how it is made so that it is highly scalable and highly performant. So we are going to get insight on this one. So this research paper link is in the description box itself. So in this video I am just going to read this entire paper word by word, no sugarcoating, not anything. So I'll just put commentary somewhere where it is needed, but most of the time it is going to be the word by word read. Okay, so maybe in later separate video I'll publish a separate summary, but this recording is going to work for me for later purpose. Wherever I want, I can listen to this one and I'll get the understanding around this one. Okay, so let's see what is the crux in, like what are the different sections in this Dynamo research paper is there. So we'll see that on a high level and we'll start reading then. Okay, so this is the first video in the engineering research paper series. So where I'm going to come up with more videos. I'll be looking around more papers around this one that is published by engineering, different engineering different companies, actually Amazon, Google, Microsoft, and many more companies, which are very good to study. Where very good case studies are there. We are going to understand that one. So let's see this Dynamo, Amazon's highly available key value store. First section is the abstract and introduction, where you will get to know about the company, the problem statement, basically what was that, and that the thing, what is the background. This is also around that information. It will build up the context, what is this all about. Then related work, what is the similar work that is available in the industry. System architecture, will see the this Dynamo's architecture. We will see like what is the interface, partitioning algorithm, what is the replication, data versioning. So you see, if you're studying this one, you should have a basic idea, like high level idea what Dynamo is. So I'll suggest that go to the website, go to Google and search about this word. So that's a prerequisite, you can say. If it is not, you will also get the understanding, not an issue. So implementation, experiences and lessons learned by this implementation, and then finally it will be concluded. So now let's move ahead and see one by one. So let's go to the abstract section and let's see what it says. So here let's go and read out the abstract sections. Reliability at massive scale is one of the biggest challenges we face at Amazon, one of the largest e-commerce operations in the world. Even the slightest outage has significant financial consequences and impact customers' trust. The Amazon.com platform, which provides services for many websites worldwide, is implemented on top of an infrastructure of tens of thousands of servers and network components located in many data centers around the world. At this scale, small and large components fail continuously, and the way persistent state is managed in the face of these failures drives the reliability and scalability of the software systems. This paper presents the design and implementation of Dynamo. A highly scalable, highly available key value storage system that Some of Amazon's core services use at some of the Amazon's core services used to provide an always on experience, that is always available experience. To achieve this level of availability, Dynamo sacrifices consistency under certain failure scenarios. It makes extensive use of object versioning and application assisted conflict resolution in a manner that provides a novel interface for developers to use. So next section is the introduction. Amazon runs a worldwide e-commerce platform that serves tens of millions of customers at peak times using tens of thousands of servers located in many data centers around the world. There are strict operational requirements on Amazon's platforms in terms of performance, reliability, and efficiency. And to support continuous growth, the platform needs to be highly scalable. Reliability is one of the most important requirements because even the slightest outage has significant financial consequences and impacts customer trust. In addition to support continuous growth, the platform needs to be highly scalable. So you see why it needs to be highly scalable, because Amazon's business is expanding on regular basis, right? So to support that business, the infrastructure down the line has to be highly scalable and on demand whenever it needs. Okay. One of the lessons organization has learned from operating Amazon's platform is that reliability and scalability of a system is dependent on how its application state is managed. Amazon uses a highly decentralized, loosely coupled services oriented architecture consisting of hundreds of services. In this environment, there is a particular need for storage technologies that are always available. For example, customers should be able to view and add items to their shopping cart even if disks are failing, network routes are flapping, or data centers are being destroyed by tornadoes. You see the extreme of the problems that is thought of here. Like, no matter what the situation is, our system should be available. Therefore, the service responsible for managing shopping carts requires that it can always write to and read from its data store, and that its data needs to be available across multiple data centers. Dealing with failures in an infrastructure comprised of millions of components is our standard mode of operations. There are always a small but significant number of servers and network components that are failing at any given time. As such, Amazon's software system needs to be constructed in a manner that treats failure handling as the normal use case. This is great. Failure handling as the normal use case without impacting availability or performance. So whenever we are building our software, so we usually test the system for when it is available and it is performing well. But here this line, like handling the failure as a normal use case and getting our system ready so that it can self heal. There is no human interaction, like human help should be needed. It should be healed automatically. To meet the reliability and scaling needs, Amazon has developed a number of storage technologies, of which Amazon Simple Storage Service, also available outside of Amazon and known as Amazon S3, is probably the best known. This paper presents the design and implementation of the Dynamo, another highly available and scalable distributed data store built for Amazon's platform. Dynamo is used to manage the state of services that have very high reliability requirements and need tight control over the trade-offs between availability, consistency, cost effectiveness, and performance. So these are the four factors: availability, consistency, cost effectiveness, and performance. Each one is very important. Amazon's platform has a very diverse set of applications with different storage requirements. A select set of applications require a storage technology that is flexible enough to let application designers configure their data store appropriately. based on these trade-offs to achieve high availability and guaranteed performance in the most cost-effective manner. There are many services on Amazon's platform that only need primary key access to a data store. For many services such as those that provide bestseller lists, shopping carts, customer preferences, session management, sales rank, and product catalog, the common pattern of using a relational database would lead to inefficiencies and limit scale and availability. Dynamo provides a simple primary key only interface to meet the requirements of these applications. Dynamo uses a synthesis of well-known techniques to achieve scalability and availability. Data is partitioned and replicated using consistent hashing. So there are different concepts that you will come across that are mainly asked in the interview questions. Okay, so by reading these papers and blogs, you will get the practical understanding where they are used, what is the practical use case, so you won't forget that anytime. So consistent hashing is one of the concepts. So I'll come to this point. So what I'm going to do the next, I'll extract these keywords, these concepts like consistent hashing, availability, cost effective, all sort of things, and I'll create separate videos on this one by referring this thing, so that will give the solid understanding about this one, right? So another concept is consistency, and consistency is facilitated by object versioning. The consistency among replicas during updates is maintained by a quorum-like technique and a decentralized replica synchronization protocol. Dynamo employs a gossip-based distributed failure detection and membership protocol. Dynamo is completely decentralized system with minimal need for manual administration. Storage needs can be added and removed from Dynamo without requiring any manual partitioning or redistribution. That is where this gossip-based protocol and consistent hashing shines, when you have to add the server into already running system, and there is, due to any failure, existing server gets removed. So they become very handy to do that automatically. So coming to the next, in the past year, Dynamo has been the underlying storage technology for a number of the core services in Amazon's e-commerce platform. It was able to scale to extreme peak loads efficiently without any downtime during the busy holiday shopping season. For example, the service that maintains shopping cart, that is shopping cart service, served tens of millions of requests that resulted in well over 3 million checkouts in a single day. And the service that managed session state handled hundreds of thousands of concurrently active sessions. So this is very important part to highlight, like at what scale it is performing actually. The main contribution of this work for the research community is the evaluation of how different techniques can be combined to provide a single highly available system. It demonstrates that an eventually consistent storage system can be used in production. This is another keyword, eventually consistent storage system can be used in production with demanding application. It also provides insight into the tuning of these techniques to meet the requirements of production system with very strict performance demands. The paper is structured in different sections. The next section that is presents the background and section 3 presents the related work, section 4 presents the system design, and section 5 describes the implementation that we saw earlier. Okay, so now let's move to the second section, that is background. Amazon's e-commerce platform is composed of hundreds of services that work in concert to deliver functionality ranging from recommendation to order fulfillment to fraud detection. Each service is exposed through a well-defined interface and is accessible over the network. These services are hosted in an infrastructure that consists of tens of thousands of servers located across many data centers worldwide. Some of these services are stateless, that is, services which aggregate response from other services, and some are stateful, that is, services that generates its response by executing business logic on its state stored in the persistent store. Traditionally, production systems store their state in relational databases for many of more common usage patterns of state persistence. However, a relational database is a solution that is far from ideal. Most of these services only store and retrieve data by primary key and do not require the complex querying and management functionality offered by an RDBMS. This excess functionality requires expensive hardware and highly skilled personnel for its operation, making it a very inefficient solution. In addition, the available replication technologies are limited and typically choose consistency over availability. Although many advances have been made in the recent years, it is still not easy to scale out database or use small partitioning schemes for load balancing. What is next? This paper describes Dynamo, a highly available data storage technology that addresses the need of these important classes of services. Dynamo has a simple key value interface, is highly available with a clear defined consistency window, is efficient in its resource usage, and has a simple scale out scheme to address growth in dataset size or request rates. Each service that uses Dynamo runs its own Dynamo instances. Next is the system assumption and requirements. The storage system for this class of service has the following requirements. First is the query model. So let's see about this one. Simple read and write operations to a data item that is uniquely identified by a key. State is stored as a binary object identified by a unique keys. No operations span multiple data items, and there is no need for relational schema. This requirement is based on the observation that a significant portion of Amazon services can work with this simple query model and do not need any relational schema. Dynamo targets applications that need to store objects that are relatively small, usually less than 1 MB. So just revisit, try to understand this one. When we are saying that relational schema is not needed, so let's see when it is needed. So let's say you are storing something in a relational database. So that means you want that data to be queried on different parameters. Let's say consider you have an employee table, you have ID, name, department, courses, categories, different parameters. At any point of time, you want to query the data based on the category, based on the name, based on the department, and different attributes. And in that case, you need that strict schema because you have that query requirement. But here with Amazon's use case, they have simple requirement that I only have a single key that I need, and against that I want to store a different attributes. So I have only one where clause. Under where clause, I'll put only single column, single attribute there. So after that, whatever value is placed, I don't care. Whoever is reading that will handle that one. So it's this map like structure, like key value. So I'll care what the key is, I'll not care what the value is. So that is what it makes it highly scalable and performant, because you are compromising that part, schema strictness, right? So you are not querying that thing. By sacrificing that, you are getting this highly performant by single key query efficiency on this one. Okay, coming to the second property, actually that is the ACID property, right? So that is transactional requirement. Atomicity, consistency, isolation, and durability. It's a set of properties that guarantee that database transactions are processed reliably. In the context of databases, a single logical operation on the data is called a transaction. Experience at Amazon has shown that data stores that provide ACID guarantees tend to have poor availability. So this is the problem that now we are seeing, that with relational database which supports transaction guarantees, they have poor availability guarantees. This has been widely acknowledged by both the industry and academia. Dynamo targets applications that operate with weaker consistency, that is part C, consistency in ACID. if this results in a highly availability. So Dynamo does not provide any isolation guarantees and permits only single key updates. So Dynamo under A said like atomicity, isolation, durability, consistency. So consistency part is sacrificed for the sake of availability. So next requirement is the that is efficiency. The system needs to function on a commodity hardware infrastructure. In Amazon's platform, services have stringent latency requirements which are in general measured at 99.9th percentile of the distribution. So understanding this latency requirement in terms of nines is yet another important thing that we should understand. Given that state access plays a crucial role in service operation, the storage system must be capable of meeting such stringent SLAs. Services must be able to configure Dynamo such that they consistently achieve their latency and throughput requirements. The trade-offs are in performance, cost efficiency, availability, and durability guarantees. What are the other assumptions that comes with it? Dynamo is used only by Amazon's internal service. Its operation environment is assumed to be non-hostile, and there are no security related requirements such as authentication and authorization. Moreover, since each service uses its distinct instance of Dynamo, its initial design targets a scale of up to hundreds of storage hosts. We will discuss the scalability limitations of Dynamo and possible scalability related extension in later sections. Coming to the next sections, that is service level agreements. What are the SLAs? To guarantee that the application can deliver its functionality in a bounded time, each and every dependency in the platform needs to deliver its functionality with even tighter bounds. Clients and service engage in a SLA, a formally negotiated contract where a client and a service agrees on several system related characteristics, which most prominently include the client's expected request rate distribution for a particular API and the expected service latency under those conditions. An example of a simple SLA is a service guarantee that it will provide a response within 300 milliseconds for 99.9% of its requests for a peak client load of 500 requests per second. So that means if the request is coming as 500 requests per second, so on average like 99.9% of the times the response time will be within 300 milliseconds. That is the SLA. In Amazon's decentralized service-oriented architecture, SLA plays an important role. For example, a page request to one of the e-commerce sites typically requires the rendering engine to construct its response by sending requests to over 150 services. These services often have multiple dependencies which frequently are other services, and such it is not uncommon for the call graph of an application to have more than one label. To ensure that page rendering engine can maintain a clear bound on page delivery, each service within the call chain must obey its performance contract. So let's see this architecture that is here. So you see these are the client requests, this is the page rendering. So you see the front end part here, then comes the request routing, then we have aggregator services, and further it is routed to different services. Then we have S3, other databases, and Dynamo instances are in picture. So you see that an abstract view of the architecture of Amazon. So whatever we see, just show we have covered this paragraph here, right? So a common approach is in the industry for forming a performance oriented SLA is to describe it using average, median, and expected variance. At Amazon, we have found that these metrics are not good enough if the goal is to build a system where all customers have a good experience rather than just the majority. For example, if extensive personalization techniques are used, then customers with longer histories require more processing, which impacts performance at the high end of the distribution. An SLA slated in terms of mean or median response times will not address the performance of this important customer segment. To address this issue, at Amazon, SLAs are expressed and measured at 99.9 percentile of the distribution. The choice for 99.9% over an even higher percentile has been made based on a cost-benefit analysis which demonstrated a significant response in cost to improve performance that much. Experience with Amazon's production systems have shown that this approach provides a better overall experience compared to those systems that meet SLA defined based on the mean or median. So mean or median and this percentile approach, they are related, and which one to choose, we just saw the what is the criteria and what is the way that you have to go. Okay. So in this paper, there are many references to this 99.9 percentile of distribution, which reflects Amazon's engineers' relentless focus on performance from the perspective of the customer's experience. Many papers report on averages, so these are included where it makes sense for comparison purposes. Nevertheless, Amazon's engineering and optimization efforts are not focused on averages. Several techniques such as the load balancing section of right coordinates are purely targeted at controlling performance at 99.9 percentile. Storage systems often play an important role in establishing a service SLA, especially if the business logic is relatively lightweight, as is the case for many Amazon services. State management then becomes the main component of a service SLA. One of the main design considerations for Dynamo is to give service control over their system properties, such as durability and consistency, and to let services make their own trade-offs between functionality, performance, and cost effectiveness. So coming to the next section, that is the design considerations. So data replication algorithm used in commercial system traditionally perform synchronous replica coordination in order to provide a strongly consistent data access interface. To achieve this level of consistency, these algorithms are forced to trade off the availability of the data under certain failure scenarios. So this is the trade-off that we should pin on in our mind, that what is the trade-off. For instance, rather than dealing with the uncertainty of the correctness of an answer, the data is made unavailable until it is absolutely certain that it is correct. From the very early replicated database works, it is well known that when dealing with the possibility of network failures, a strong consistency and high data availability cannot be achieved simultaneously. So there is always compromise between consistency and availability. As such, systems and applications need to be aware which properties can be achieved under which conditions. For systems prone to server and network failures, availability can be increased by using optimistic replication techniques, where changes are allowed to propagate to replicas in the background and concurrent disconnected work is tolerated. The challenge with this approach is that it can lead to conflicting changes which must be detected and resolved. This process of conflict resolution introduces two problems. This process of conflict resolution introduces another two problems. What are those problems? Let's see. When to resolve them and who resolves them. Dynamo is designed to be an eventually consistent data store, that is, all updates reach all replicas eventually. An important design consideration is also to decide when to perform the process of resolving update conflicts, that is, whether conflicts should be resolved during read or writes. Many traditional data stores execute conflict resolution during writes and keep the read complexity simple. In such systems, Writes may be rejected if the data store cannot reach all or majority of the replicas at a given time. On the other hand, Dynamo targets the design space of an always writable data store. That is, write won't fail. That is, data store that is highly available for writes for a number of Amazon services. Rejecting customer updates could result in a poor customer experience. For instance, the shopping cart service must allow customers to add and remove items from their shopping cart even amidst network and server failures. This requirement forces us to push the complexity of conflict resolution to the read side in order to ensure the writes are never rejected. So the next design choice is who performs the process of conflict resolutions. This can be done by the data store or the application. If conflict resolutions are done by the data store, its choices are rather limited. In such cases, the data store can only use simple policies such as last write bins to resolve conflicting updates. On the other hand, since the application is aware of the data schema, it can decide on the conflict resolution method that is best suited for its client's experience. For instance, the application that maintains customer shopping cart can choose to merge the conflicting versions and return a single unified shopping cart. That means if I have added an item which is not replicated to all the instances and I have done another write which is in some other instance, like when I'm reading it, I don't want to lose I can, it's not an issue if I see all the items, but I don't want to miss any item from my cart or wish list that is there. So the merging can be done here. Despite this flexibility, some application developers may not want to write their own conflict resolution mechanism and choose to push it down to the data store, which in turn chooses a simple policy such as last write bins. Other key principles embraced in the design are incremental scalability. Dynamo incremental scalability, that is, Dynamo should be able to scale out one storage host, henceforth referred to as node, at a time with minimal impact on both operators of the system and the system itself. Second is the symmetry. So under symmetry, what we are saying, like every node in the Dynamo should have the same set of responsibility as its peers. There should be no distinguished node or nodes that takes special roles or extra set of responsibility. In our experience, symmetry simplifies the process of system provisioning and maintenance. Decentralization is another key characteristics. So what it says, an extension of symmetry is the decentralization. The design should favor decentralized peer-to-peer techniques over centralized control. In the past, centralized controller has resulted in the outages, and the goal is to avoid it as much as possible. This leads to a simpler, more scalable and more available systems. Next characteristics, the heterogeneity. The system needs to be able to exploit heterogeneity in the infrastructure it runs on. Example, the work distribution must be proportional to the capabilities of the individual servers. This is essential in adding new nodes with higher capacity without having to upgrade all the hosts at once. So that is it about the second section that we covered a lot. The next section is about the related work. So let's see. The first one, under related work, we are going to see the peer-to-peer systems. Yes, so moving to the next section, here we are going to see what are the related works that is more or less similar to Dynamo that we have. So first one in that series is peer-to-peer systems. There are several peer-to-peer systems that have looked at the problem of data storage and distribution. The first generation of P2P systems such as Freenet and how to pronounce it, Nutella, or were predominantly used as a file sharing systems. These were examples of unstructured P2P networks where the overlay links between the peers were established arbitrarily. In these networks, a search query is usually flooded through the network to find as many peers as possible that share the data. P2P systems evolved to the next generation into what is widely known as structured P2P networks. These networks employ a globally consistent protocol to achieve that any node can efficiently route a search query to some peer that has the desired data. Systems like Pastry and CORD use routing mechanisms to ensure that queries can be answered within a bounded number of hops. To reduce additional latency introduced by multi-hop routing, some P2P systems employ order of one routing, O of one routing, where each peer maintains enough routing information locally so that it can route requests to access a data item to the appropriate peer within a constant number of hops. So these are the references that we will go and see this. Various storage systems such as Ocean Store and PAST were built on top of these routing overlays. Ocean Store provides a global transactional persistent storage service that supports serialized updates on widely replicated data to allow for concurrent updates while avoiding many of the problems inherent with wide area locking. It uses an update model based on conflict resolution. Conflict resolution was introduced to reduce the number of transactions aborts. Ocean Store resolves conflicts by processing a series of updates, choosing a total order among them, and then applying them atomically in that order. It is built for an environment where the data is replicated on an untrusted infrastructure. By comparison, PAST provides a simple abstraction layer on top of Pastry. For persistent and immutable objects, it assumes that application can build the necessary storage semantics such as mutable files on top of it. On this related work, we have second in the category, that is distributed file systems and databases. Distributed data for performance, availability and durability has been widely studied in the file system and database systems community. Compared to P2P storage system that only supports flat namespaces, distributed file systems typically support hierarchical namespaces. Systems like Ficus and Coda replicate files for high availability at the expense of consistency. Update conflicts are typically managed using specialized conflicts resolution procedures. The Farsight system is a distributed file system that does not use any centralized server like NFS. Farsight achieves high availability and scalability using replication. The Google file system is another distributed file system built for hosting the state of Google's internal applications. GFS uses a simple design with a single master server for hosting the entire metadata and where the data is split into chunks and is stored in the chunk server. Another is Bayou. Bayou is a distributed relational database system that allows disconnected operations and provides a eventual consistency. Among these, Bayou, Coda and Ficus allow disconnected operations and are resilient to issues such as network partitions and outages. These systems differ on their conflict resolution procedures. For instance, Coda and Ficus perform system level conflict resolution and Bayou always allows application level resolutions. All of them, however, guarantee eventual consistency. Similar to these systems, Dynamo allows read and write operations to continue even during network partitions and resolves update conflicts using different conflict resolution mechanisms. Distributed block storage systems like Fab, which splits large size objects into smaller blocks and stores each block in a highly available manner. In comparison to these systems, a key value store is more suitable in this case because it is intended to store relatively small objects. Second point, key value stores are easier to configure on a per application basis. Antiquity is wide area distributed storage system designed to handle multiple server failures. It uses a secure log to preserve data integrity, replicates each log on multiple servers for durability, and uses Byzantine fault tolerance protocol to ensure data consistency in contrast to Antiquity. Dynamo does not focus on the problem of data integrity and security and is built for a trusted environment. Bigtable is a distributed storage system for managing structured data. It maintains a sparse multidimensional sorted map and allows applications to access their data using multiple attributes. Compared to Bigtable, Dynamo targets application that require only key value access with primary focus on high availability where updates are not rejected even in the wake of network partition or server failures. So this is the ring that you were seeing, that partitioning and replication of keys in Dynamo ring. So this is the ring of the consistent hashing. So what happens, like A, B, C, D, E, F, G that you are seeing, these are the different servers on the system, and whenever any key, you see, any put item or any item is request is coming to store the data, so that data will be stored on one of these nodes. So how to determine which node that key is going to be stored? That is where that is calculated by hash is calculated, that key hash is calculated, and the number of systems that we have, that number is divided, then we can get the instance where it is going to store. So whatever value that come, that will be on that ring, so on that server that is stored in that range. Okay, so you see node B, C and D store keys in range A, B including. So when that instance is calculated, that is to be stored at A, so for availability and redundancy purpose, so that same data is replicated to nearest nodes like B, C and D also as per the configuration. Okay, so that if something goes wrong with node A, the data is safe with other nodes. Traditional replicated relational database systems focus on the problem of guaranteeing strong consistency to replicated data. Although strong consistency provide the application writer a convenient programming model, these systems are limited in scalability and availability. These systems are not capable of handling network partitions because they typically provide strong consistency guarantees. On the related work side, next section is the discussion. Dynamo differs from the aforementioned decentralized storage system in terms of its target requirements. First, Dynamo is targeted mainly at applications that need an always writable data. So that is the use case for the Dynamo. Data store where no updates are rejected due to failures or concurrent writes. This is a crucial requirement for Amazon application. Second, as noted earlier, Dynamo is built for an infrastructure within a single admin dominance Second is as noted earlier, Dynamo is built for an infrastructure within a single administrative domain where all nodes are assumed to be trusted. So this assumption is there that all the nodes are trusted, so we can get rid of all the security features that we have to employ. Third is the applications that use Dynamo do not require support for hierarchical namespaces, a norm in many file systems, or complex relational schema. Fourth is the Dynamo is built for latency sensitive applications that require at least 99.9% of read and write operations to be performed within a few hundred milliseconds. To meet these stringent latency requirements, it was imperative for us to avoid routing requests through multiple nodes, which is the typical design adopted by several distributed hash tables such as CORD and PASTRY. This is because multi-hop routing increases variability in response times, thereby increasing the latency at higher percentiles. Dynamo can be characterized as a zero-hop DHT, where each node maintains enough routing information locally to route a request to the appropriate node directly. So basically client has that information which node to go for the specific key that they are looking for. So they save that hop time. So the next section is system architecture. Pretty good concepts, pretty good things are coming in place in this one here. The architecture of a storage system that needs to operate in a production setting is complex. In addition to the actual data persistent component, the system needs to have scalable and robust solutions for load balancing, membership and failure detections, failure recovery, replica synchronizations, overload handling, state transfer, concurrency and job scheduling, request marshalling, request routing, system monitoring and alarming, and configuration management. There is a lot of lists that is required, right? This is worth highlighting. Describing the details of each of the solutions is not possible, so this paper focuses on the core distributed system techniques used in Dynamo, like partitioning replication, versioning, membership, failure handling and scaling. So these are the concept, these are the things that this paper will focus on. We will see more about it. So see, this table is very important. So this is the summary of the techniques that is in the DynamoDB and what are their advantages and what is their basically advantage. Only three things are there. So partitioning problem is there. So that is what is the technique that is employed here. Consistent hashing is used. So what is the advantage? Incremental scalability. So any node can come and go. There is no human intervention is needed. That is done automatically. High availability for writes. Vector clocks with reconciliation during reads. Version size is decoupled from update rates. Handling temporal failures, sloppy quorum and hinted handoff technique is used. Provides high availability and durability guarantee when some of the replicas are not available. Recovering from permanent failures, anti-entropy using Merkle tree. So there are two. Temporary failure and permanent failure. So these are the sloppy quorum hinted handoff. Anti-entropy using Merkle tree is being in place. So what is the benefit? Synchronizes divergent replicas in the background. So next is the membership and failure detection problem. So gossip based membership protocol and failure detection is there. This preserves symmetry and avoids having a centralized registry for storing membership and node liveness information. Okay, so next section, that is where under this system architecture, what is the section? System architecture, we have a system interface. Dynamo stores object associated with the key through a simple interface. It exposes two operations, get and put. The get operation locates the object replicas associated with the key in the storage system and returns a single object or a list of objects with conflicting versions along with the context. The put operation, key, context and object operation, determines where the replicas of the objects should be placed based on the associated key and writes replicas to a disk. The context encodes system metadata about the object that is opaque to caller and includes information such as the version of the object. The context information is stored along with the object so that the system can verify the validity of the context object supplied in the put request. Dynamo treats both key and the object supplied by the caller as an opaque array of bytes. It applies a MD5 hash on the key to generate a 128-bit identifier, which is used to determine the storage node that are responsible for serving the key. This is worth highlighting. Second is the partitioning. We saw the system interface. Second is the partitioning algorithm. One of the key design principle requirement for Dynamo is that it must scale incrementally. This requires a mechanism to dynamically partition the data over the set of nodes, that is the storage host. Dynamo's partitioning scheme relies on consistent hashing to distribute the load across multiple storage systems. In consistent hashing, the output range of a hash function is treated as a fixed circular space or ring. That is, the largest hash value wraps around to the smallest hash value, so it forms a ring. So if you are familiar with the hash table, you can relate it. Hash table grows incrementally, when as per the number of rows that we have in the table. So there is a definite end in the hash table. In consistent hashing, there is no end, it is a circle. So whatever after the highest value comes the lowest value, that node gets connected. Each node in the system is assigned a random value within this space which represents its position on the ring. Each data item identified by a key is assigned to a node by hashing the data item's key to yield its position on the ring and then walking the ring clockwise to find the first node within a position larger than item's position. Thus, each node becomes responsible for the region in the ring between it and its predecessor node on the ring. The principal advantage of consistent hashing is that departure or arrival of a node only affects its immediate neighbors and other nodes remain unaffected. The basic consistent hashing algorithm presents some challenges. First, the random position assignment of each node on the ring leads to non-uniform data and load distribution. Second, the basic algorithm is oblivious to the heterogeneity in the performance of nodes. To address these issues, Dynamo uses a variant of consistent hashing. So see, now the customization as per the use case is starting. Consistent hashing is a generic concept, but how to utilize that for our purposes. So see what customization is there. Instead of mapping a node to a single point in the circle, each node gets assigned to multiple points in the ring. So if there is one physical server in the ring, that will be represented by multiple nodes. Okay, so to this end, Dynamo uses the concept of virtual nodes. A virtual node looks like a single node in the system, but each node can be responsible for more than one virtual node. Effectively, when a node is added to the system, it is assigned multiple positions, henceforth tokens, in the ring. The process of fine-tuning Dynamo's partitioning scheme is discussed in the section 6 that we will see eventually. Using virtual nodes has the following advantages. If a node becomes unavailable due to failures or routine maintenance, the load handled by this node is evenly dispersed across the remaining or available nodes. Second is, when a node becomes available again or a new node is added to the system, the newly available node accepts a roughly equivalent amount of load from each of other nodes. Third is that the number of virtual nodes that a node is responsible can be decided based on its capacity, accounting for heterogeneity in the physical infrastructure. So that is about consistent hashing and virtual nodes that is in place for the DynamoDB. Next is the replication. To achieve high availability and durability, Dynamo replicates its data on multiple hosts. Each data item is replicated at n hosts, where n is a parameter configured per instance. Each key, k, is assigned to a coordinator node described in the previous section. The coordinator is in charge of the replication of the data items that fall within its range. In addition to locally storing each key within its range, the coordinator replicates these keys at the n-1 clockwise successor nodes in the ring. This results in a system where each node is responsible for the region of the ring between it and its nth predecessor. In figure 2 that we saw the concept like ring circle like structure, node B replicates the key at node C and D in addition to storing it locally. Node D will store the key that fall in the range A, B, B, C and C, D. The list of nodes that is responsible for storing a particular key is called the preference list. The system is designed as will be explained in the section 4.8, so that every node in the system can determine which nodes should be in this list for any particular key. To account for node failures, preference list contains more than n nodes. Note that the use of the virtual nodes, it is possible that the first n successor position for a particular key may be owned by less than n distinct physical nodes. That is, a node may hold more than one of the first n positions. To address this, the preference list for a key is constructed by skipping positions in the ring to ensure that the list contains only distinct physical nodes. Next concept is the data versioning. Dynamo provides eventual consistency, which allows for updates to be propagated to all replicas asynchronously. A put call may return to its caller before the update has been applied to all the replicas, which can result in scenarios where a subsequent get operation may return an object that does not have the latest updates. If there are no failures, then there is a bound on the update propagation times. However, under certain failure scenarios, that is server outages or network partitions, updates may not arrive at all replicas for an extended period of time. There is a category of applications in Amazon's platform that can tolerate such inconsistencies and can be constructed to operate under these conditions. For example, the shopping cart application requires that an add to cart operation can never be forgotten or rejected. If the most recent state of the cart is unavailable and the user makes changes to an older version of the cart, that change is still meaningful and should be preserved. But at the same time, it shouldn't supersede the currently unavailable state of the cart, which itself may contain changes that should be preserved. Note that both add to cart and delete item from cart operations are translated into put request to the Dynamo. When a customer wants to add an item or remove from a shopping cart and the latest version is not available, the item is added to or removed from the older version and the divergent versions are reconciled later. In order to provide this kind of guarantee, Dynamo treats the result of each modification as new and immutable version of the data. It allows for multiple versions of an object to be present in the system at the same time. Most of the time, new versions subsume the previous version and the system itself can determine the authoritative version, syntactic reconciliation. However, version branching may happen in the presence of failures combined with concurrent updates resulting in conflicting versions of an object. In these cases, the system cannot reconcile the multiple versions of the same object, and the client must perform the reconciliation in order to collapse multiple branches of data evolution back into one. A typical example of a collapse operation is merging different versions of a customer shopping cart. Using this reconciliation mechanism, an add to cart operation is never lost. However, deleted items can resurface. It is important to understand that certain failure modes can potentially result in the system having not just two but several versions of the same data. Updates in the presence of a network partition and node failures can potentially result in an object having distinct version subhistories, which system will need to reconcile in the future. This requires us to design applications that explicitly acknowledge the possibility of multiple versions of the same data in order to never lose any updates. Dynamo uses vector clocks in order to capture causality, not the casuality, but it is causality between different versions of the same object. A vector clock is effectively a list of node, like this is the structure, a list of node and counter pairs. One vector clock is associated with every version of every object. One can determine whether two versions of an object are on parallel branches or have a causal ordering by examining their vector clocks. If the counters of the first object's clocks are less than or equal to all of the nodes in the second clock, then the first is an ancestor of the second and can be forgotten. Otherwise, the two changes are considered to be in conflict and require reconciliation. In Dynamo, when a client wishes to update an object, it must specify which version it is updating. This is done by passing the context it obtained from an early read operation, which contains the vector clock information. Upon processing a request, if Dynamo has access to multiple branches that cannot be syntactically reconciled, it will return all the objects at the leaves with the corresponding version information in the context. An update using this context is considered to have reconciled the divergent versions and the branches are collapsed into a single new version. To illustrate the use of vector clocks, let us consider the example shown in figure 3. A client writes figure 3 is this one, by the way. So pause the video and just set this in mind. Like, this is the write handled by this node SX, that is there. D1 is there, write handled by SX. Again, it is D2, so it is fine that SX2 will override this one. Now, this SX2, like this write handled by SY node. And again, another write is there which is handled by Z. And now reconciled and written by SX, SX3, SY, SZ1, version evolution of an object over time. So this is how it is happening. So see, the node SX that handles the write for this key increases its sequence number and uses it to create the data's vector clock. The system now has the object D1 and its associated clock, that is SX1. The client updates the object. Assume the same node handles this request as well. The system now also has object D2 and its associated clock. D2 descends from D1 and therefore overrides D1. However, there may be replicas of D1 lingering at nodes that have not yet seen D2. Let us assume that the same client updates the object again and a different server, say SY, handles the request. The system now has the data D3 and is associated clock SX to SY1. Next, assume a different client reads D2 and it then tries to update it. And another node, say SZ, does the write. The system now has D4, descendant of D2, whose version clock is now SX2 and SZ1. Alright, just try to recall in the mind. A node that is aware of D1 or D2 could determine upon receiving D4 and its clock that D1 and D2 are overwritten by the new data and can be garbage collected, D1 and D2, because they were sequential increments. A node that is aware of D3 and receives D4 will find that there is no causal relations between them. Causal relation, like this D3 and D4, there is no relation, direct relation. They are related by D2. In other words, there are changes in D3 and D4 that are not reflected in each other. Both versions of the data must be kept and present to a client upon read for semantic reconciliation. Now assume some client reads both D3 and D4. The context will reflect that both values were found by the read. The read's context is a summary of the clock of D3 and D4, namely SX2, SY1, SZ1. If the client performs the reconciliation and node SX coordinates the write, SX will update its sequence number in the clock. The new data from D3 and D4 will have the following clock: SX3, SY1, SZ1. A possible issue with vector clock is that the size of the vector clocks may grow if many servers coordinate the writes to an object. In practice, this is not likely possible. This is not likely because the writes are usually handled by one of the top n nodes in the preference list. In case of network partitions or multiple server failures, write requests may be handled by nodes that are not in the top n nodes in the preference list, causing the size of the vector clocks to grow. In these scenarios, it is desirable to limit the size of vector clock. To this end, Dynamo employs the following clock truncation mechanism. Along with each node counter pair, Dynamo stores a timestamp that indicates the last time the node updated the data item. When the number of node counter pairs in the vector clock reaches a threshold, say 10, the oldest pair is removed from the clock. Clearly, this truncation scheme can lead to inefficiencies in reconciliation as the descendant relationship cannot be derived accurately. However, this problem has not surfaced in production and therefore this issue has not been thoroughly investigated. Next is the execution of get and put operations. Any storage node in Dynamo is eligible to receive client, get and put operations for any key. In this section, for sake of simplicity, we describe how these operations are performed in a failure-free environment, and in subsequent sections, we describe how read and write operations are executed during failures. Both get and put operations are invoked using Amazon's infrastructure specific request processing framework over HTTP. There are two strategies that a client can use to select a node. First, route its request through a generic load balancer that will select a node based on the load information, or two, use a partition aware client library that routes request directly to the appropriate coordinator node. The advantage of the first approach is that client does not have to link any code specific to Dynamo in its application, whereas the second strategy can achieve lower latency because it skips a potential forwarding step. A node handling a read or write operation is known as the coordinator. Typically this is the first among the top n nodes in the preference list. If the requests are received through a load balancer, request to access a key may be routed to any random node in the ring. In this scenario, the node that receives the request will not coordinate it if the node is not in the top n of the request key preference list. Instead, that node will forward the request to the first among the top n nodes in the preference list. Read and write operations involve the first n healthy nodes in the preference list, skipping over those that are down or inaccessible when all nodes are healthy. The top n nodes in the key's preference list are accessed. When there are node failures or network partitions, nodes that are lower ranked in the preference list are accessed. To maintain consistency among its replicas, Dynamo uses a consistency protocol similar to those used in the quorum system. This protocol has two key configurable values, R and W, that is read and write. R is the read operation, R is the minimum number of nodes that must participate in a successful read operation. W is the minimum number of nodes that must participate in a successful write operation. Setting R and W setting R and W such that R plus W greater than N. N is the total number of nodes. R is the that we just see, like just keep this in mind, like R is the minimum number of nodes that has to perform for a successful read. W is the minimum number of nodes that has to respond for a successful write operation. Addition of these two should be greater than N, which yields a quorum-like system. In this model, the latency of a get operation is dictated by the slowest of read or write replicas. For this reason, R and W are usually configured to be less than N to provide a better latency. Upon receiving a put request for a key, the coordinator generates the vector clock for the new version and writes the new version locally. The coordinator then sends the new version. So this is very important, like before sending it to further, it writes that locally, along with the new vector clock to the n highest ranked reachable nodes. If at least W-1 nodes respond, then the write is considered as successful. Similarly, for a get request, the coordinator requests all existing versions of the data for that key from the n highest ranked reachable nodes in the preference list for that key, and then waits for R responses before returning the result to the client. If the coordinator ends up gathering multiple versions of the data, it returns all the versions it deems to be causally unrelated. The divergent versions are then reconciled, and the reconciled version superseding the current version is written back. Awesome. Next concept is the handling failures, that is hinted handoff. It is going to take care of the temporary failure. If Dynamo used a traditional quorum approach, it would be unavailable during server failures and network partitions and would have reduced durability even under the simplest of failure conditions. To remedy this, it does not enforce strict quorum membership and instead it uses a sloppy quorum. All read and write operations are performed on the first n healthy nodes from the preference list, which may not always be the first n nodes uncounted while working the consistent hashing ring. Consider the example of a Dynamo configuration given in figure 2. With n is equal to 3, in this example, if node A is temporarily down or unreachable during a write operation, then a replica that would normally have lived on A will now be sent to D. This is done to maintain the desired availability and durability guarantees. The replica sent to D will have a hint in its metadata that suggests which node was the intended recipient of the replica, in this case A. Even if it is going some other node, it will have that metadata, where I belong originally. Nodes that received hinted replicas will keep them in a separate local database that is scanned periodically. Upon detecting that A has recovered, D will attempt to deliver the replica to A. Once the transfer succeeds, D may delete the object from its local store without decreasing the total number of replicas in the system. Using hinted handoff, Dynamo ensures that read and write operations are not failed due to temporary node or network failures. Applications that need the highest level of availability can set W to 1, which ensures that a write is accepted as long as single node in the system has durably written the key in its to its local store. Thus, the write request is only rejected if all the nodes in the system are unavailable. However, in the practice, most Amazon services in production set a higher W to meet the desired level of durability. If a more detailed discussion of configure NR and W is following in the section 6, it is imperative that a highly available storage system be capable of handling the failures of an entire data centers. Data center failures happen due to power outages, cooling failures, network failures, and natural disasters. Dynamo is configured such that each object is replicated across multiple data centers. In essence, the preference list of a key is constructed such that the storage nodes are spread across multiple data centers. These data centers are connected through high-speed network links. This scheme of replicating across multiple data centers allows Amazon to handle entire data center failures without a data outage. Awesome. We saw the temporary failure. What about the permanent failures? Handling permanent failures, that is replica synchronization. Hinted handoff works best if the system membership churns is low and node failures are transient. There are scenarios under which hinted replicas become unavailable before they can be returned to the original replica node. To handle this and other threats to durability, Dynamo implements an anti-entropy replica synchronization protocol to keep the replicas synchronized. To detect the inconsistencies between replicas faster and to minimize the amount of transfer data, Dynamo uses Merkle tree. A Merkle tree is a hash tree where leaves are hashes of the values of the individual keys. Parent nodes higher in the tree are hashes of their respective children. The principal advantage of Merkle tree is that each branch of the tree can be checked independently without requiring nodes to download the entire tree or the entire dataset. Moreover, Merkle trees help in reducing the amount of data that needs to be transferred while checking the inconsistencies among replicas. For instance, if the hash values of the root of two trees are equal, then the values of the leaf nodes in the tree are equal and the nodes require no synchronization. If not, it implies that the values of some replicas are different. In such cases, the nodes may exchange the hash values of a children and process continues until it reaches the leaves of the trees. at which point the host can identify the keys that are out of sync. Merkle tree minimizes the amount of data that needs to be transferred from synchronization and reduce the number of disk reads performed during the anti-entropy process. Dynamo uses Merkle trees. Dynamo uses Merkle trees for anti-entropy as follows. Each node maintains a separate Merkle tree for each key range, the set of keys recovered by a virtual node it hosts. This allows nodes to compare whether the keys within a key range are up to date. In this scheme, two nodes exchange the root of the Merkle tree corresponding to the key ranges that they host in common. Subsequently, using the tree traversal scheme described above, the nodes determine if they have any differences and perform the appropriate synchronization action. The disadvantage with this scheme is that many key ranges change when a node joins or leaves the system, thereby requiring the trees to be recalculated. This issue is addressed, however, by the refined partitioning scheme described in the upcoming section. We saw the failure, permanent and temporary failures. Second is the membership and failure detection, because we have that consistent hashing ring, right? So a node can go down and a new node can be added when the demand increases. So how to detect that removal and addition, that is where is covered in the membership and failure detection. Ring membership, first one is the ring membership. In Amazon's environment, node outages due to failures and maintenance tasks are often transient but may last for extended intervals. A node outage rarely signifies a permanent departure and therefore should not result in rebalancing of the partition assignment or repair of the unreachable replicas. Similarly, manual error could result in the unintentional startup of new Dynamo nodes. For these reasons, it was deemed appropriate to use an explicit mechanism to initiate the addition and removal of the nodes from a Dynamo ring. An admin uses a command line tool or a browser to connect to a Dynamo node and issue a membership change to join a node to a ring or remove a node from a ring. The node that serves the request writes the membership change and its time of issue to persistent store. The membership changes form a history because nodes can be removed and added back multiple times. A gossip-based protocol propagates membership changes and maintains an eventually consistent view of membership. Each node contacts a peer chosen at random every second, and the two nodes efficiently reconcile their persistent membership change histories. When a node starts for the first time, it chooses its set of tokens. It starts with a set of tokens, virtual nodes in the consistent hash space, and maps nodes to their respective token sets. The mapping is persisted on disk. On disk, and initially contains only the local node and token set. The mappings stored at different Dynamo nodes are reconciled during the same communication exchange that reconciles the membership change histories. Therefore, partitioning and placement information also propagates via gossip-based protocol, and each storage node is aware of the token ranges handled by its peers. This allows each node to forward a keys read-write operations to the right set of the node directly. Next is the external discovery. The mechanism described above could temporarily result in a logically partitioned Dynamo ring. For example, the admin could contact node A to join A to the ring, then contact node B to join B to the ring. In this scenario, nodes A and B would each other consider itself a member of the ring, yet neither would be immediately aware of the other. To prevent logical partitions, some Dynamo nodes play a role of seed nodes. Seeds are nodes that are discovered by an external mechanism and are known to all nodes. Because all nodes eventually reconcile their membership with the seed, logical partitions are highly unlikely. Seeds can be obtained either from a static configuration or from a configuration service. Typically, seeds are fully functional nodes in the Dynamo ring. Great. Failure detection, how it is detected. Failure detection in Dynamo is used to avoid attempts to communicate with unreachable peers during get and put operations and when transferring partitions and hinted replicas. For the purpose of avoiding failed attempts at communication, a purely local notion of failure detection is entirely sufficient. Node A may consider node B failed if node B does not respond to node A's message, even if B is responsive to node C message. In the presence of a steady rate of client requests generating inter-node communication in the Dynamo ring, a node A quickly discovers that node B is unresponsive when B fails to respond to a message. Node A then uses alternate nodes to service requests that map to B's partition. A periodically retries B to A periodically retries B to check for the latter's recovery in the absence of client requests to drive traffic between two nodes. Neither node really needs to know whether the other is reachable and responsive. Decentralized failure detection protocols use a simple gossip style protocol that enable each node in the system to learn about the arrival or departure of other nodes. For detailed information on decentralized failures detectors and the parameters affecting their accuracy, the interested reader is referred to number 8. There is a reference that can be read. Early designs of Dynamo used a decentralized failure detector to maintain a globally consistent view of failure state. Later, it was determined that the explicit node join and leave methods obviates the need for a global view of failure state. This is because nodes are notified of permanent node additions and removals by the explicit node join and leave methods, and temporary node failures are detected by the individual nodes when they fail to communicate with others while forwarding requests. So that is about that one. So next section is the adding, removing storage nodes. When a new node is added into the system, it gets assigned a number of tokens that are randomly scattered on the ring. For every key range that is assigned to node X, there may be a number of nodes less than or equal to n that are currently in charge of handling keys that fall within its token range. Due to the allocation of key ranges to X, some existing nodes no longer have to let's read it again. Due to the allocation of key ranges to X, some existing nodes no longer have to sum of their keys, and these nodes transfer these keys to X. Let's read it early. So let us consider a simple bootstrapping scenario where node X is added to the ring shown in figure 2 between A and B. When X is added to the system, it is in charge of storing in the ranges F, G, G, and AX, which comes clockwise in direction. As a consequence, nodes B, C, and D no longer have to store the keys in these respective ranges. Therefore, nodes B and C will offer to and upon confirmation from X transfers the appropriate set of keys. When a node is removed from the system, the reallocation of keys happens in the reverse process. Operational exercise has shown that this approach distributes the load of key distribution uniformly across the storage nodes, which is important to meet the latency requirements and to ensure fast bootstrapping. Finally, by adding a confirmation round between the source and the destination, it is made sure that a destination node does not receive any duplicate transfer for the given key range. So that's what covers our section 4. Next is the implementation, which I'm going to start recording after a break. So it is taking too much time. Actually, it should take time because there is a lot to grasp in this one, right? So whatever I'm reading, that it's not just that reading out. So I think it's the second or third time that I'm reading it. Okay, so it's going through in my mind. It's a sort of mind map is there. So same is the expectation when you are reading it, if you have heard so far. Okay, so we'll cover implementation in some time. So now let's read about the implementation part. In Dynamo, each storage node has three main software components. The first one is the request coordination, membership, and failure detection, and a local persistent engine. All these components are implemented in Java. It's good to know that Dynamo internally is implemented in Java. Three components: request coordination, membership and failure detection, local persistent engine. Dynamo's local persistent component allows for different storage engines to be plugged in. Engines that are in use are Berkeley database, transactional data store, Berkeley database, Java edition, MySQL, and in-memory buffer with persistent backing store. The main reason for designing a pluggable persistent component is to choose the storage engine best suited for an application's access pattern. For instance, BDB, that is Berkeley database, can handle objects typically in the order of tens of kilobytes, whereas MySQL can handle objects of larger size. Applications choose Dynamo's local persistent engine based on their object size distribution. The majority of Dynamo's production instances use BDB transactional data store. The request coordination component is built on top of an event-driven messaging substrate where the message processing pipeline is split into multiple stages similar to SCADA architecture. All communications are implemented using Java NIO channels. The coordinator executes the read and write request on behalf of clients by collecting data from one or more nodes in the case of reads, or storing data at one or more nodes for writes. Each client request results in the creation of a state machine on the node that received the client request. The state machine contains all the logic for identifying the nodes responsible for a key, sending the request, waiting for response, potentially doing retries, processing the replies, and packaging the response to the client. Each state machine instance handles exactly one client request. For instance, a read operation implements the following state machine: send read request to the nodes, wait for the minimum number of required responses. If too few replies were received within a given time bound, fail the request. Fourth is otherwise gather all the data versions and determine the ones to be returned, and if versioning is enabled, perform syntactic reconciliation and generate an opaque write context that contains the vector clock that subsumes all the remaining versions. For the sake of brevity, the failure handling and retry states are left out from these details whatever we see, but it gives the idea how it is implemented. After the read response has been returned to the caller, the state machine waits for a small period of time to receive any outstanding response. If stale versions were returned in any of the response, the coordinator updates those nodes with the latest version. This process is called read repair because it repairs replicas that have missed a recent update at an opportunistic time and relieves the entropy protocol from having to do it. As noted earlier, write requests are coordinated by one of the top n nodes in preference list, although it is desirable always to have the first node among the top n to coordinate the writes, thereby serializing all writes at a single location. This approach has led to uneven load distribution resulting in SLA violations. This is because the request load is not uniformly distributed across objects. To counter this, any of the top n nodes in the preference list is allowed to coordinate the writes. In particular, since each write usually follows read operations, the coordinator for a write is chosen to be node that replied fastest to the previous read operation, which is stored in the context. Information of the request, information of the request. This optimization enables us to pick the node that has data that was read by the preceding read operations, thereby increasing the chances of getting read your writes. That is, read your writes consistency, that is what was written will be read. It also reduces variability in the performance of the request handling, which improves the performance at 99.9 percentile. So number 6 section comes here, like experience and lessons learned. Dynamo is used by several services with different configurations. These instances differ by their version reconciliation logic and read-write quorum characteristics. The following are the main patterns in which Dynamo is used. First pattern is the business logic specific reconciliation. This is popular use case for Dynamo. Each data object is replicated across multiple nodes. In case of divergent versions, the client application performs its own reconciliation logic. The shopping cart service discussed earlier is a prime example of this category. Its business logic reconciles objects by merging different versions of a customer's shopping cart. What is the next lesson that was learned out of this? And these are some diagrams that are given, like direct DB rights and some matrices are there. So let's study this as well. This is important. So what is given? Average and 99.9 percentile of latencies for read and write requests during our peak request season for December 2006. This is a pretty old one. The intervals between consecutive ticks in the x-axis correspond to 12 hours. Latencies follow a diurnal pattern similar to the request rate, and 99.9 percentile latencies are an order of magnitude higher than averages. So you see this graph, like timeline, and this 99.9 writes, this is there, 99 point reads are there, average writes are there, this one is there, and average reads are there. This is black and white, a bit less clear, but it gives an idea, like direct BDB writes and buffer writes matrix it is given here. Comparison of performance of 99.9 percentile latencies for buffered versus non-buffered writes over a period of 24 hours. The intervals between consecutive ticks in the x-axis correspond to 1 hour. Okay, so now second business use case is time instant based reconciliation. This case differs from the previous use only in the reconciliation mechanism. In case of divergent versions, Dynamo performs simple time instant based reconciliation logic of last write bins. That is, the object with the largest physical time instant value is chosen as the correct version. The service that maintains customer session information is a good example of a service that uses this mode. High performance read engine. While Dynamo is built to be an always writable data store, a few services are tuning its quorum characteristic and using it as a high performance read engine. Typically, these services have a high read request rate and only a small number of updates. In this configuration, typically R is set to be 1 and W to be N for these services. Dynamo provides the ability to partition and replicate their data across multiple nodes, thereby offering incremental scalability. Some of these instances function as an authoritative persistent cache for data stored in more heavyweight backing stores. Services that maintain product catalog and promotional items fit in this category. The main advantage of Dynamo is that its client application can tune the value of N, R, and W. R is the minimum number of instances that to be read for the successful read. W is the minimum number of write nodes that has to respond for the write to be successful, and N is the total number of nodes instances in the cluster. Availability and durability. For instance, the value of N determines the durability of each object. A typical value of N used by Dynamo's users is 3. The value of W and R impact object availability, durability, and consistency. For example, if W is set to 1, then the system will never reject a write request as long as there is at least one node in the system that can successfully process a write request. However, low values of W and R can increase the risk of inconsistency, as write requests are deemed successful and returned to the clients even if they are not processed by a majority of the replicas. This also introduces a vulnerability window for durability when a write request is successfully returned to the client, even though it has been persisted at only a small number of nodes. Next, traditional wisdom holds that durability and availability go hand in hand. However, this is not necessarily true here. For instance, the vulnerability window for durability can be decreased by increasing W. This may increase the probability of rejecting requests, thereby decreasing availability because more storage hosts need to be alive to process a write request. The common NRW configuration used by several instances of Dynamo is 322. These values are chosen to meet the necessary levels of performance, durability, consistency, and availability SLAs. All the measurements presented in this section were taken on a live system operating with a configuration of 322. and running a couple of hundred nodes with homogeneous hardware configuration. As mentioned earlier, each instance of Dynamo contains nodes that are located in multiple data centers. These data centers are typically connected through high-speed network links. Recall that to generate successful GET or PUT response R or W, nodes need to respond to the coordinator. Clearly, the network latencies between data centers affect the response time and the nodes and their data center locations are chosen such that the application's target SLAs are met. So that's about the this lessons learned under lesson learns. We have seen this, and this is the graph that you can see. Fraction of nodes that are out of balance, that is nodes whose request load is above a certain threshold from the average system load, and their corresponding request the between ticks in excess correspond to a period of 30 minutes. So moving ahead with the next section, that is balancing performance and durability. While Dynamo's principal design goal is to build a highly available data store, performance is an equally important criterion in Amazon's platform. As noted earlier, to provide a consistent customer experience, Amazon's services set their performance targets at higher percentiles, such as 99.9 or 999.99 percentile. A typical SLA required of services that use Dynamo is that 99.9% of the read and write requests execute within 300 milliseconds. Since Dynamo is run on standard commodity hardware components that have far less I/O throughput than high-end enterprise servers, providing consistently high performance for read and write operations is a non-trivial task. The involvement of multiple storage nodes in read and write operations makes it even more challenging, since the performance of these operations is limited by the slowest of the R or W replicas. Figure above shows the average and 99.9 percentile latencies of Dynamo's read and write operations during a period of 30 days. As seen in the figure, the latencies exhibit a clear diurnal pattern, which is result of the diurnal pattern in the incoming request rate. That is, there is a which is the indicator of that is a significant difference in a request rate between the daytime and night. Moreover, the write latencies are higher than read latencies, obviously because write operations always result in disk access. Also, the 99.9 percentile latencies are around 200 milliseconds and are an order of magnitude higher than the averages. This is because the 99.9 percentile latencies are affected by several factors such as variability in the request load, object size, and locality patterns. While this level of performance is acceptable for a number of services, a few customer-facing services required higher levels of performance. For these services, Dynamo provides the ability to trade off durability guarantees for performance. In the optimization, each storage node maintains an object buffer in its main memory. Each write operation is stored in the buffer and gets periodically returned to a storage by a writer thread. So let's read it again. This is important. While this level of performance is acceptable for a number of services, a few customer-facing services required higher levels of performance. For these services, Dynamo provides the ability to trade off durability guarantees for performance. In the optimization, each storage node maintains an object buffer in its main memory. Each write operation is stored in the buffer and gets periodically returned to storage by a writer thread. In this scheme, read operations first check if the requested key is present in the buffer. If so, the object is read from the buffer instead of storage engine. Good. This optimization has resulted in lowering the 99.9 percentile latency by a factor of 5 during peak traffic, even for a very small buffer of 1000 objects. Also as seen in the figure, write buffering smooths out higher percentile latencies. Obviously, this scheme trades durability for performance. In this scheme, a server crash can result in missing writes that were queued up in the buffer. To reduce the durability risk,
The write operations is refined to have the coordinator choose one out of the n replicas to perform a durable write. Since the coordinator waits only for W responses, the performance of the write operation is not affected by the performance of the durable write operations performed by a single replica. Coming to the next section, that is ensuring uniform load distribution. Dynamo uses consistent hashing to partition its key space across its replicas and to ensure uniform load distribution. A uniform key distribution can help us achieve uniform load distribution, assuming the access distribution of keys is not highly skewed. In particular, Dynamo's design assumes that even where there is a significant skew in access distribution, there are enough keys in the particular end of the distribution so that the load of handling popular keys can be spread across the nodes uniformly through partitioning. This section discusses the load imbalances seen in the Dynamo and the impact of different partitioning strategies on load distribution. To study the load imbalance and its correlation with request load, the total number of requests received by each node was measured for a period of 24 hours. Broken down into interval of 30 minutes, in a given time window, a node is considered to be in balance if the node's request load deviates from the average load by a value less than a certain threshold. Here 15%, otherwise the node was deemed out of balance. Figure 6 represents the fraction of nodes that are out of balance, henceforth imbalance ratio. During this time period, for reference, the corresponding request load received by the entire system during this time period is also plotted. As seen in the figure, the imbalance ratio decreases with increasing load. For instance, during low loads, the imbalance ratio is as high as 20%, and during high loads, it is close as 10%. Intuitively, this can be explained by the fact that under high loads, a large number of popular keys are accessed, and due to uniform distribution of keys, the load is evenly distributed. However, during low loads, where load is 1/8, what happens in that case? So these are the diagrams that it was referring. Actually, fewer popular keys are accessed, resulting in a higher load imbalance. This section discusses how Dynamo's partitioning scheme has evolved over time and its implication on load distribution. Strategy 1. T random tokens per node and partition by token value. This was the initial strategy deployed in prod and described in section previous. In this scheme, each node is assigned T tokens chosen uniformly at random from a hash space. The tokens of all nodes are ordered according to their values in the hash space. Every two consecutive tokens define a range. The last token and the first token form a range that wraps around from the highest value to the lowest value in the hash space. Because the tokens are chosen randomly, the ranges vary in size. As nodes join and leave the system, the token set changes and consecutively the range change. Note that the space needed to maintain the membership at each node increases linearly with the number of nodes in the system. While using this strategy, the following problems were encountered. First, when a new node joins the system, it needs to steal its key ranges from other nodes. However, the nodes handing the key ranges off to the new node have to scan their local persistence store to retrieve the appropriate set of data items. Note that performing such a scan operation on a production node is tricky, as scans are highly resource intensive operations and they need to be executed in the background without affecting the customer performance. This requires us to run the bootstrapping task at the lowest priority. However, this significantly slows the bootstrapping process, and during busy shopping season when the nodes are handling millions of requests a day, the bootstrapping has taken almost a day to complete. Second, when a node leaves the system, the key ranges handled by many nodes change and the Merkle trees for the new ranges need to be recalculated, which is a non-trivial operation to perform on a production system. Finally, there was no easy way to take a snapshot of the entire key space due to the randomness in the key ranges, and this made the process of archival complicated. In this scheme, archiving the entire key space requires us to retrieve the keys from each node separately, which is highly inefficient. The fundamental issue with this strategy is that with that scheme for the data partitioning, data placement are intertwined. For instance, in some cases it is preferred to add more nodes at this to the system in order to handle an increase in the request load. However, in this scenario, it is not possible to add nodes without affecting data partitioning. Ideally, it is desirable to use independent schemes for partitioning and placement. To this end, following strategies were evaluated. T random tokens per node and equal sized partitions. In this strategy, the hash space is divided into Q equally sized partition ranges and each node is assigned T random tokens. Q is usually set such that Q greater than N and Q this S into T, where S is the number of nodes in the system. In this strategy, the tokens are only used to build the function that maps values in the hash space to the ordered list of nodes and not to decide the partitioning. A partition is placed on the first n unique nodes that are encountered while walking the consistent hashing ring clockwise from the end of the partition. Illustrates the strategy for n is equal to 3. In this example, nodes A, B, C are encountered while walking the ring from the end of the partition that contains key K1. Okay. The primary advantage of this strategy are decoupling of partitioning and partition placement, enabling the possibility of changing the placement scheme at runtime. So this was the diagram. Strategy 3, this is the strategy 2, this is the strategy 1. So key 1 is going to be here, then ABC, key 1 is here, ABC is here, key 1 is ABC is here. Okay. Got that. So coming to the third one, QS tokens per node equal sized partitions. Similar to the strategy 2, this strategy divides the hash space into equally sized partitions and the placement of partition is decoupled from the partitioning scheme. Moreover, each node is assigned QS tokens, where S is the number of nodes in the system. When a node leaves the system, its tokens are randomly distributed to the remaining nodes such that these properties are preserved similarly. When a node joins the system, it steals tokens from the nodes in the system in a way that preserves these properties. Okay. The efficiency of these three strategies is evaluated for a system with S is equal to 30 and N is equal to 3. However, comparing these different strategies in a fair manner is hard, as different strategies have different configurations to tune their efficiency. For instance, the load distribution property of strategy 1 depends on the number of tokens, while strategy 3 depends on the number of the partition, that is Q. One fair way to compare these strategies is to evaluate the skew in their load distribution, while all strategies are the same amount of space to maintain their membership information. For instance, in strategy 1, each node needs to maintain the token position of all the nodes in the ring, and in the strategy 3, each node needs to maintain the information regarding the partitions assigned to each node. In our next experiment, these strategies were evaluated by varying the relevant parameters T and Q. The load balancing efficiency of each strategy was measured for different sizes of membership information that needs to be maintained at each node, where load balancing efficiency is defined as the ratio of average number of requests served by each node to the maximum number of requests served by the hottest node. Okay. The results are given in figure 8. As seen in the figure, strategy 3 achieves the best load balancing efficiency and strategy 2 has the worst load balancing efficiency. For a brief time, strategy 2 served as an interim setup during the process of migrating Dynamo instances from strategy 1 to 3. Compared to strategy 1, strategy 3 achieves better efficiency and reduces the size of membership information maintained at each node by 3 orders of magnitude. While storage is not a major issue, the nodes gossip the membership information periodically, and as such, it is desirable to keep this information as compact as possible. In addition to this, strategy 3 is advantageous and simpler to deploy for the following reasons. Faster bootstrapping recovery. Since partition ranges are fixed, they can be stored in separate files. Maintaining a partition can be relocated as a unit by simply transferring the file. avoiding random access needed to be located at specific times. This simplifies the process of bootstrapping and recovery. Ease of archival. Periodical archiving of the dataset is a mandatory requirement for most of AWS services. Archiving the entire dataset stored by Dynamo is simpler in strategy 3 because the partition files can be archived separately. By contrast, in strategy 1, the tokens are chosen randomly and archiving the data stored in Dynamo requires retrieving the keys from individual nodes separately and is usually inefficient and slow. The disadvantage of strategy 3 is that changing the node membership requires coordination in order to preserve the properties required of the assignment. Okay, good one. So let's see this diagram. So strategy 1 is there, strategy 2, strategy 3. Strategy 3 is this color, so that is 0.9, 0.8, and this is the strategy 2, efficiency, and 5,000, 10,000, and this size of metadata maintained at each node in abstract minutes. Okay, got that. So moving to the next section, that we have divergent versions, when and how many. As noted earlier, Dynamo is designed to trade off consistency for availability. To understand the precise impact of different failures on consistency, detailed data is required on multiple factors: outage length, type of failure, component reliability, workload, etc. Presenting these numbers in detail is outside of the scope of this paper. However, this section discusses a good summary metric: the number of divergent versions seen by the application in a live production environment. Divergent versions of a data item arises in two scenarios. The first is when the system is facing failure scenario, such as node failures, data center failures, and network partitions. The second is when the system is handling a large number of concurrent writers to a single data item and the multiple nodes end up coordinating the updates concurrently. From both a usability and efficiency perspective, it is preferred to keep the number of divergent versions at any given time as low as possible. If the versions cannot be syntactically reconciled, because on vector clocks alone, they have to be passed to the business logic for semantic reconciliation. Semantic reconciliation introduces additional load on services, so it is desirable to minimize the need for it. In our next experiment, the number of versions returned to the shopping cart service was profiled for a period of 24 hours. During this period, 99.94% of requests saw exactly one version, that is this. Requests saw 3 versions, and this percent of requests saw 4 versions. So this number is percentage is quite low. This shows that divergent versions are created rarely. Experience shows that the increase in the number of divergent versions is contributed not by failures but due to the increase in number of concurrent writers. The increase in the number of concurrent writers is usually triggered by busy robots, automated client programs, and rarely by humans. So this issue is not discussed in detail due to the sensitive nature of the story. Moving to the next section, that we have client driven or server driven coordination. As mentioned in above section 5, Dynamo has a request coordination component that uses state machines to handle incoming requests. Client requests are uniformly assigned to nodes in the ring by a load balancer. Any Dynamo node can act as a coordinator for a read request. Write request, on the other hand, will be coordinated by a node in the key's current preference list. This restriction is due to the fact that these preferred nodes have the added responsibility of creating a new version stamp that causally subsumes the version that has been updated by the write request. Note that if Dynamo's versioning scheme is based on the physical timestamp, any node can coordinate a write request. An alternative approach to request coordination is to move the state machine to the client nodes. In this scheme, client applications use a library to perform request coordination locally. A client periodically picks a random Dynamo node and downloads its current view of Dynamo membership state. Using this information, the client can determine which set of nodes from the preference list for any given key. Read request can be coordinated at the client node, thereby avoiding the extra network hop that is incurred if the request were assigned to a random Dynamo node by the load balancer. Writes will either be forwarded to a node in the keys preference list, or they can be forwarded to a node in the preference list, or they can be coordinated locally if Dynamo is using time instant based versioning. So this diagram is the performance of a client driven and server driven coordination approach. You see, server driven millisecond 68.9, 99.9th percentile, write latency 68.5, average read latency 3.9, average write latency 4. So whenever it is a server driven, all the time it is higher on a higher end than the client driven approach. An important advantage of the client driven coordination approach is that load balancer is no longer required to uniformly distribute client load. Fair load distribution is implicitly guaranteed by the near uniform assignment of keys to the storage nodes. Obviously, the efficiency of this scheme is dependent on how fresh the membership information is at the client. Currently, client polls a random Dynamo node every 10 seconds for membership updates. A pull-based approach was chosen over a push-based one, as the former scales better with large number of clients and requires very little state to be maintained at the servers regarding clients. However, in the worst case, the client can be exposed to stale membership for duration of 10 seconds. In case if the client detects its membership table is stable, for instance, when some members are unreachable, it will immediately refresh its membership information. The above table shows the latency improvements at 99.9th percentile and averages that were observed for a period of 24 hours using client-driven coordination compared to the server-driven. As seen in the table, the client-driven coordination approach reduces the latencies by at least 30 milliseconds for 99.9th percentile and decreases the average by 3 to 4 milliseconds. The latency improvement is because the client-driven approach eliminates the overhead of the load balancer and the extra network hop that may be incurred when a request is assigned to a random node. As seen in the table, average latencies tends to be significantly lower than latencies at 99.9th percentile. This is because Dynamo's storage engine, caches and write buffer have good hit ratios. Moreover, since the load balancers and network introduce additional variability to the response time, the gain in response time is higher for 99.9th percentile than average. So that was that comparison, like client and server initiated approaches. So next section is the balancing background versus foreground tasks. Each node performs different kinds of background tasks for replica synchronization and data handoff, either due to hinting or adding removing nodes in addition to its normal foreground operations. In early production settings, these background tasks trigger the problem of resource contention and affect the performance of the regular put and get operations. Hence, it became necessary to ensure that background tasks ran only when the regular critical operations are not affected significantly. To this end, the background tasks were integrated with an admission control mechanism. Each of the background tasks uses this controller to reserve runtime slice of the resources, example database. Shared across all background. A feedback mechanism based on the monitored performance of the foreground task is employed to change the number of slices that are available to background tasks. The admission controller constantly monitors the behavior of the resource access while executing a foreground put get operation. Monitored aspects include latencies for disk operations, failed database access due to log contention and transaction timeouts, and request queue wait times. This information is used to check whether the percentile of latencies or failures in a given trailing time window are close to a desired threshold. For example, the background controller checks to see how close the 99th percentile database read latencies over the last 60 seconds is to a preset threshold by say 50 milliseconds. The controller uses such comparison to assess the resources availability for the foreground operations. subsequently decides on how many times slices will be available to background tasks, thereby using the feedback loop to limit the intrusiveness of the background activities. Note that a similar problem of managing background tasks has been studied in section 4. So, final point is discussion. This section summarizes some of the experiences gained during the process of implementation and maintenance of Dynamo. Many Amazon internal services have used Dynamo for the past 2 years, and it has proved significant levels of availability to its applications. In particular, applications have received successful responses without timing out for 99.9995% of its requests, and no data loss event has occurred to date. Awesome. Moreover, the primary advantage of Dynamo is that it provides the necessary knobs using the 3 parameters NRW to continue their instance based on their needs. Unlike popular commercial data stores, Dynamo exposes data consistency and reconciliation logic issues to the developers. At the outset, one may expect that the application logic to become more complex. However, historically, Amazon's platform is built for high availability, and many applications are designed to handle different failure modes and inconsistencies that may arise. Hence, porting such applications to use Dynamo was a relatively simple task. For new applications that want to use Dynamo, some analysis is required during the initial stages of the development to pick the right conflict resolution mechanism that meet the business case appropriately. Finally, Dynamo adopts a full membership model where each node is aware of the data hosted by its peers. To do this, each node actively gossips the full routing table with other nodes in the system. This model works well for a system that contains a couple of hundreds of nodes. However, scaling such a design to run with tens of thousands of nodes is not trivial, because the overhead in maintaining the routing table increases with the system size. This limitation might be overcome by introducing hierarchical extensions to Dynamo. Also note that this problem is actively addressed by order of 1 O1 DST systems. Conclusion. This is the final section, so we have come to the end. So if you have reached so far, this is great. What to say, like it has taken me quite a time to complete this recording. Okay, so you see couple of times reading before starting recording, and one whole day to record this one in different iterations. So let's cover the final shot, that is conclusion. This paper described Dynamo, a highly available and scalable data store used for storing state of a number of core services of Amazon's e-commerce platform. Dynamo has provided the desired levels of availability and performance and has been successful in handling server failures, data center failures, and network partitions. Dynamo is incrementally scalable and allows service owners to scale up and down based on their current request load. Dynamo allows service owners to customize their storage systems to meet their desired performance, durability, and consistency SLAs by allowing them to tune the parameters NR and W. The production use of Dynamo for the past year demonstrate that decentralized techniques can be combined to provide a single highly available system. Its success in one of the most challenging application environments shows that an eventually consistent storage system can be building block for highly available applications. So that is the conclusion. So final section in research paper comes with the acknowledgement and references. So so for a research paper, we should like continuously spend at least a week of time to grasp everything that they have there, like in terms of references, some of the terms that we do not know, we all should understand that. So with that, I'll conclude this video. It's I think more than about 2 hours of video that I'm going to upload. So yeah, I'll be coming up next. I'll be uploading the summary of this video, like bytes, like in 10 minutes of video. We'll extract the important pieces in 10 minutes and we'll upload that one. Okay, so see you, take care, bye bye.